This lesson is for section 9.8. It's the last section of this chapter, and today we're going to be solving systems of quadratics. So solving a system is not something that's a new concept for us. We actually began the year solving linear systems, and if you recall, when we solve linear systems, we could have three different possibilities. If both equations are lines, then they could have one solution because they could intersect once. They could never intersect, meaning they're parallel lines with no solution to the system. Or they could in fact be the same line with an infinite number of solutions. If you recall, we use two methods to solve those systems. We either use substitution or elimination. Now it's also possible to have something called a quadratic linear system. In that case, you're going to see one equation that represents a conic and the other equation represents a line. Now, as you can see from the pictures in the diagram, we can have three different possibilities for the types of intersections that you would see. Now today we're going to be working with systems of quadratics, so we're going to see more than one conic section, and as you can see from the diagrams, there are different possibilities for the number of intersections that will occur. So one of the things that we're going to want to do today is to verify the number of solutions that we get by drawing a quick sketch of the system. Alright, let's get started with our very first example. Now one of the things I like to do before I begin a problem is to try to identify the type of shape I'm looking at. So I look at each equation and I try to decide what conic this would be. So right away, when I see the top line here has two different variables squared, I know it can't be a parabola, so I throw that one out. I also notice that both of the coefficients are positive, which means it can't be a hyperbola. So I know I for sure don't have a hyperbola. So I'm down to the circle or the ellipse. Now if you recall, a circle always has the same coefficients in front of both the x squared and the y squared term. So in this case it can't be a circle, it must be an ellipse. Now if we look at the bottom line here, I notice that I have a negative in front of that y squared term, so I know this is going to be a hyperbola. You got to be careful though, because sometimes there might be more than one negative in the equation, so you might want to look at the final standard form of that equation before you determine which type of conic you're looking at. Okay, so now let's try to get started with actually solving this system. Now your two methods are still the same. You can either use substitution or you can use elimination. Now in this case, I recognize that elimination would be really easy for me here because I can eliminate the x squared term here if I just multiply everything in the bottom line by -1. Now when I try to add these two lines together, I have those two canceling, so 0x squared, and then 5y squared minus a -y squared gives me 6y squared. 98 minus 2 gives me 96. So I end up with y squared equaling 16. Now you have to be really careful here because there's actually two possibilities for what y could equal. Y could equal positive or -4 here. So this is why a system of quadratics is actually really interesting, because when you deal with the linear system, you never get two possibilities for your y or your x value. Here we have two different possibilities and we're going to have two different equations that we're going to solve. So we have two cases. One, if y is equal to 4, or if y is equal to -4. Now we're going to solve these separately, okay? But I always want you to start by writing in your two cases. So let's start with our first case here when y is equal to 4. Now when you solve the rest of the system here, it's going to be just like any normal system. You plug that value back into the original equations. Now you can do it in either the top line or the bottom line. I'm just going to choose to use the bottom line. So we end up with an equation 2x squared minus, when I plug in y squared here, I get 16. So 2x squared minus 16 equals 2. And if I solve here and divide, we end up with two unique solutions as well for x. X could equal positive or -3. So you got to be careful here that you don't just say 3. There are two possibilities for x. Now remember, the solutions to this particular system that we're solving algebraically, these represent the coordinates of the points where your ellipse and your hyperbola will intersect. So these are really actually coordinates. So I have the x coordinate 3 and the y coordinate up here 4, as well as another point with an x coordinate of -3 and a y value of 4. So we have so far two unique points where our ellipse and our hyperbola will intersect. Alright, now we can work with case 2. So if y is equal to -4, we solve the system one more time just by plugging this value in. It doesn't matter which line you choose. Let's do the bottom line one more time. Here, if we plug in -4, we still get 2x squared minus 16 equals 2. Okay, if we plug in a -4 here, we still have the sign out in front that's still negative. Okay, now if we solve, we already know the solutions here. The solutions to this equation are positive and -3. So let's interpret one more time how to write our actual coordinates. So our x value could be +3, but our y value has to stay -4. Okay, so we have 3, -4, and we have another point because x could also equal -3, while the y will stay -4. So here we have an additional 2 points where the ellipse and the hyperbola will intersect. So each of these points represents a solution to our system, so let's make sure that we're really clear about identifying each and every single one of these. I'm going to list all of them together, okay, because some of you guys are going to have work all over your paper. Just make sure that in the end you box all of your final points, okay. These each represent one of the intersections for the ellipse and the hyperbola. So we do require that you provide a rough sketch to accompany those solutions that you just found, and we're not looking for a beautiful diagram here. We don't want to see like the asymptotes or the foci or anything like that. You're just going to show the general shape. So when I look at both of these equations, they're actually both centered at the origin, and when I look here, this has a negative in front of the y squared, so that hyperbola is going to open left to right. So this is literally all I'm going to do to sketch that. Okay, the hyperbola that opens left to right. And for the ellipse here, it's elongated in the x direction, and you can actually verify that if you put it into standard form. And then I'm just going to label the points of intersection here. This point has to be the point 3, 4. This point has to be the coordinate 3, -4. This point here has to be the coordinate -3, 4. And this point here has to have both negatives, -3 and -4, just because of where they lie in the particular quadrants. So this is a sketch, and this would be the entire solution that you need to provide when you're solving this particular system. All right, moving on now to example 2. Let's identify the shapes in this particular system. So in the first equation listed, this is going to be a circle because both coefficients are positive and they are the same coefficients. So I have a circle here. And you can complete the square if you really wanted to. You don't have to just verify that that's the case, but this is going to be a circle. Now the bottom equation is another ellipse, and it doesn't have pretty values underneath for the r sub x squared or the r sub y squared, but it's still an ellipse. Now with this particular system, if you notice I have this note written over here on the right, you don't want to eliminate the x squared term. You can't eliminate your x's because if you try to do something like, let's say, multiply by -5 on the top line to try to eliminate those x squareds, the x squared will definitely get, you can get rid of that, but no matter what you do, you'll still have a linear term here left over. So you'll have the 9y squared plus a -5y squared, so you would get 4y squared here. Then you would have an 80x that you would have to bring down with another constant over here. And as you can see, you can't solve this equation because you still have two different variables, so it doesn't get you anywhere to try to eliminate the x. Instead, you'll have to eliminate the y. So we'll multiply the top line so that we can get the same coefficient here. We'll multiply by -9. So now we have -9x squared, -9y squared, positive 144x, and -39 times 9 is 351, I think, I hope. Let me pause. Okay, yes, it was 351. All right, so now what we're going to do is add these two lines together, all right? Clearly the 9y squared and the -9y squared, those will cancel out, and what's great about that is we no longer have any y left over whatsoever. Everything else in our equation will be left in terms of x. So if I take 5x squared and subtract 9x squared, I end up with -4x squared. The 144x has nothing to add to in the top equation here, so I just bring down that 144x. Then I'll add 161 in this 351. That gives me 512. And then now I'm just going to solve what is a quadratic. So as soon as you get down to one variable, then you know you're in the right track. If you still have x's and y's, you're doing something wrong, okay? So I'm going to pause and then solve this system. Or I'm sorry, solve this quadratic. Alright, so as you can see, after I've gone ahead and factored that trinomial here, I end up with two unique solutions. X can equal 32 and x equals 4. So just like we did in the last example, what we're going to do is set up two different cases. Case 1 is if x is 32. So we'll go ahead and we'll solve by plugging in x equals 32 back into either of the equations. Now I'm going to choose the bottom equation just because here you have two different places where you'd have to plug in x. So I'm just going to be a little bit lazy. It doesn't matter though. Again, it doesn't matter where you choose to plug it in. So we'll plug it into the bottom. So we should have 5 times x is now 32, so 32 squared plus 9y squared equals 161. So I'm going to go ahead again and pause this and solve. So as you can see, I end up with the equation y squared is equal to -551. Now if I want to solve completely for y, I have to get y alone by square rooting both sides. The problem is I can't take the square root of a negative. Remember, that's an imaginary number. So this has no real solutions. Okay? Meaning when x is 32, it does not produce any coordinates where your graph of the circle and the ellipse will intersect. So now we move on to the second case. We're going to say what happens when x is 4. Okay, so if x is 4, we do the same thing. We're going to plug that value in, and one more time I'll just do it in the bottom equation because, again, I'm lazy. So I'll pause and solve. So now when I plug in x equals 4, we end up with the equation y squared is equal to 9. And if I go ahead and solve for y here, I have two possible values. Y is equal to positive 3 and negative 3. So when I interpret my answer, remember, this is when x is 4. So we have the coordinate 4, positive 3, and 4, negative 3. Okay, so the points of intersection, or let's call them solutions, are at 4, 3, and 4, negative 3. Make sure you always box this and are really clear about where you're saying those graphs intersect. Okay, we're actually going to leave our sketch for in class tomorrow. So we found already our points of intersection for the graph of this circle and the ellipse, and tomorrow you'll see visually where they actually intersect. Alright, in our next example, we're looking at the equation of an ellipse in the top line. We have positive coefficients in front of an x squared and a y squared term, and they are also different from one another, so that means it can't be a circle. Okay. Now in the bottom line, you're looking at neither of these two being quadratic, so we're looking at the equation of a line. So this is a linear equation below. Now in this particular problem, we cannot use elimination, and because we can't use elimination, we have to use substitution, which does require a little bit more work. But the reason why you can't use elimination here is because let's say you try to eliminate the x's. Okay, so I'm looking to eliminate the x. Well, obviously there is no x squared term below, so I can't do anything that way. I would have to maybe multiply by negative 2 in order to eliminate the 10x and the negative 10x here. So let's say I do that. I have negative 10x, then plus 8y equals positive 2. Well, now when I try to cancel out some terms here, the 10x does cancel, but when I add everything else, I still have this 5x squared term. And the same thing would happen if I tried to eliminate the y. So elimination here fails to work. So using substitution requires us to solve for one variable, okay, either the x or the y. Now in the top line here, I can't solve for x or y. There's just too much going on here. So I'm going to solve for either x or y in the bottom equation. So if I were to isolate the x, I would move over that 4y, okay, and I would then divide by 5. So I have x equals 4y minus 1 over 5. Now with substitution, you just plug this value into the other equation wherever you see an x. So I see an x twice, right here and right here. So I'm going to go ahead and just make that substitution. 4y minus 1 over 5 now becomes the x in the equation above. Alright, so I've made that substitution into the top line, and now comes kind of the more difficult part, just because you're going to have a lot of work to do in order to simplify this equation and solve for y. So I'm going to go ahead and pause and then show some of the work here. Alright, so in my first step, I haven't really done much. I've just squared both the numerator here and the denominator, and then I can simplify this a little bit further and call that 4y minus 1 squared over 5. Then over here, 10 over that 5, I've rewritten that as just 2 times 4 minus 1. So I'm going to go ahead, again, pause, and then simplify a little bit further. Alright, in my next step, I haven't really done much. I'm just simplifying here and distributing that too. But now what I'm going to do is move each of these terms to the other side, okay? Alright, so as you can see, I've moved over those terms, and now what I'm going to do to try to get rid of this 5 in the denominator, I'm going to go ahead and multiply by 5 on both sides of this equation. So I'm going to multiply all of these by 5 as well. Alright, so I've distributed the 5 here to each of those terms on the right hand side, and then on the left hand side those 5's will cancel, and then I've gone ahead and FOILed the left hand side. So I have this quadratic left over. Now I'm going to go ahead and factor and try to solve this quadratic. Alright, so hopefully you're pausing and you are copying down this work. I figured that taking you through step by step would be really long in this particular problem, and solving the quadratic isn't the hard part. The hard part is understanding how you're supposed to interpret your solutions. So we do get two unique solutions here. Y is equal to 4 and y is equal to negative 1. So remember, we have to set up two different cases. We have one case if y is equal to 4. So what we're going to do is plug that in back into the original equations. Now it doesn't matter which one you plug it into, but I would plug it into the bottom one, because then I don't have to deal with multiple variables in a quadratic. If I plugged it into the top, I still have an x and an x squared left over, and I don't want to deal with that. Okay, so I'm going to plug it into the bottom equation. So if 5x minus 4 times 4 equals negative 1, and we add that 16 over here, we will end up with x equaling 3. So this is not two solutions, right? It's just one. And when we interpret this, we end up with one coordinate here, or one point, and the coordinates of that point are 3, 4. All right, remember, we also have another value for y here. Y can also equal -1. So let's let y equal -1. In that case, 5x minus 4 times -1 should equal -1. And if we solve here, we end up with x equaling 1. So we have another point of intersection. That point of intersection will be the point 1, -1. So we've got two different places. So I'm going to write this off. Points of intersection. So we have 3, 4, and 1, -1. So our ellipse and our line intersect exactly twice. Okie dokie, artichokes. I've decided that this problem is a little bit too tough to try to fit into a video. I'd rather take our time with it and kind of discuss this as a class and go more in depth with this example. So this example problem is to be continued tomorrow in class first thing. So make sure you're ready to work and ready to ask good questions. Nice job. See you mañana.